arch. In its many forms, this uniquely adaptable and robust shape has dominated the Western world since its invention over 2,000 years ago. Its characteristics: able to span long stretches, carry incredible loads, and withstand the ravages of time, all while being composed of the simplest materials, make it the most enduring building form known to man.
The idea behind an arch is that it channels the force that the structure needs to support in a way that is most efficient in terms of the way it uses the material.
No other shape comes close to the arch and its relatives, the vault, cylinder, and dome, for efficiency. But there was a time when such structures were unknown.
To imagine that you were alive 2,000 years ago and you wanted to build a bridge across a relatively wide stream. Your choices weren't very many. You could fell a tree if the stream was narrow, and you could build a bridge by walking across the tree. The tree would then be what engineers call a beam.
This simple idea, the beam, had been in use since at least 12,000 BC at Stonehenge on the windswept plains of southern Britain. Beams, or lintels, spanned moderately spaced pillars in this ancient structure. The Greeks later used this method of construction for temples. It was practical and could be beautiful, but was limited to the width that a wood or stone beam could span before it collapsed. But somewhere, sometime in the ancient world, someone realized that there was a better way to build grand yet practical structures. Unfortunately, building materials in the ancient world had limitations, forcing early architects to be creative.
The constraint that the Romans had to operate under was the availability of materials. You can't build beams out of blocks of rock. You could build beams out of timber that was available to the Romans, but again, you were limited to very short spans. So by necessity, they had to discover a new structural form, a shape, which would generate only compressive forces for which both rock and concrete were ideal materials. And the innovativeness of Roman engineers that discovered that the arch was the ideal form for that time and still is an ideal form for our time.
They took an old and simple idea and built a civilization upon it. But what really makes this form so wondrous?
The simple idea of the hanging chain really illustrates all of the main structural principles of an arch. And it's much easier to visualize. So here we have a force and tension, and if you could stand on your head or freeze this and turn it over, you could picture exactly what's happening to the forces in an arch. And again, the key idea is that this string, it never makes a mistake. It never lies and is always finding the pure tension form because the string can only carry tension. In the same way, a masonry structure is a material that doesn't lie and can only carry compression.
The arch can carry enormous weight and is purely a compression structure. That is, it can withstand pressure. The more force that's applied, the more compressed the arch becomes. On the other hand, if you apply tension to it, it loses its strength rapidly. As the legs of the arch begin to spread, the arch can collapse. The secret of stability in arch design is to contain the forces, or the line of thrust as it's called, within the arch.
As we move supports around, the arch can adjust to these different movements and can adapt with new internal forces. And the key really, or the magic, is that they can carry so many different possible loadings. And as the ground moves, the arch quite happily adjusts to it. It's in equilibrium, it stands. We can find a line of forces through one.
As long as the line of force is contained inside the structure of the arch, or terminates at the arch supports, it can stand practically forever. But if the line of force moves outside the arch, because of increased loads or changes in shape, it will fail. The Romans understood this
is a tribute to the fact that the Roman engineers knew about how their structures could redistribute forces even after they become damaged.
Arches come in all sizes, shapes, and styles. The classic Romanesque arch is a semicircle, built of stone or concrete. The Gothic arch from the 12th to 15th centuries has a pointed crown, allowing for more open spaces. Other arches include the basket handle arch, popular in Britain, which allowed a very broad opening. And in the East, overextended or Moorish arches appeared, with less structurally sound, but unique-looking forms. Although an arch's primary purpose is to support a load, its shape invited artistic innovations. As arch design progressed, the use of stone became a highly refined craft. The placement of stones, and especially the keystone, became a personal statement of the designer. A keystone is the last stone placed in a traditional arch. It's the stone that locks the arch into place. Keystones were traditionally made larger and more important looking than the other voussoirs, or arch stones. But surprisingly, this was largely a cosmetic choice.
You hear a lot of talk about the keystone in an arch being this most critical piece, this most special piece. The keystone has the smallest amount of force, yet it gets all of this attention. It's kind of a paradox. You'd expect to have more force at the middle, but the smallest force is at the middle. And therefore, a keystone does not actually carry very much force. If you have an odd number of voussoirs, they're called the pieces of an arch, then there is an odd one in the middle, which is the keystone. If, however, you make the arch out of an even number, then there is no keystone.
But being the last stone in the arch, the keystone does have one very special purpose. Without it, the arch will fall down. The ancient Romans were the first to make structural use of the arch in large buildings and bridges, and solved some of the great building problems of their day. But other obstacles remained.
Another great challenge that the Roman engineers faced was how do you carry water over long distances, and particularly over valleys. And you see these enormous structures, several tiers high. And in their aqueducts, they typically began with larger spans at the bottom and went to smaller and smaller spans at the top to reduce the amount of material at the top. And also because a smaller arch is more stable than a longer span arch. They're very stable, and then they load the bigger arches near the base of the aqueduct, and those arches are made stable by the surcharge of all of the arches above them.
The Pont du Gard aqueduct in France is almost 1,000 feet long and 160 feet high, with arches on the bottom level ranging from 50 to 70 feet wide and 65 feet high. The uppermost arches are only 10 feet wide and 28 feet high.
The purpose of an arch is twofold: to change direction of applied force, number one, and number two, to make sure that the forces that are now going in a different direction are in compression.
These astounding structures were a stunning testament to the ingenuity of their designers. But there was much more to come from the basic design of the aqueduct.
I think of the Colosseum kind of as a Roman aqueduct that's folded onto itself to enclose space.
It was the arena of the emperor and the citizens of Rome. Over 600 feet across at its widest point and 160 feet high, the Colosseum was home to myriad events. It allowed up to 75,000 spectators to watch great gladiatorial battles in architectural splendor.
The use of concrete is perhaps the most exciting aspect of Roman building technology. The arch is a structural form. It would work with concrete or it would work with rock or masonry, but the Romans took the arch to another level.
The Roman invention and use of concrete for construction led to the development of another use of the arch, the barrel vault.
So instead of a single arch now, you have a room with a series of arches, and so that's three-dimensional, it's a vault. But the Romans went way beyond that. They also took arches and they turned some arches 90 degrees to the first and made intersecting arches. So it's as if you took two barrel vaults and intersected them. And in the middle, you have a big open area that's a groin vault. That's a clear Roman innovation.
Impressive though it is, the Colosseum was just a precursor for more remarkable structures to come. Just across Rome, the Pantheon was built in 125 AD. This innovative building would set the standard for centuries to come.
One sees structures like the Pantheon, and the most shocking, breathtaking aspect of walking into a structure like that is open space. What domes afford is interior space unencumbered by column support. The columns, of course, or the walls are on the periphery of the dome, and they're transmitting all the compression force from the dome down through the walls into the foundation.
The roof of the Pantheon was the world's first large dome. It was an unprecedented accomplishment.
You could think of a dome as a series of arches that are all leaning on each other in the middle. But in addition to that, a dome acts as a series of hoops that surround the dome. So what prevents the dome from falling inward, there are arches in plan that are really circles that also can carry load in each ring of the dome as you build up.
The Pantheon has a traditional temple entrance, which opens to the great dome-covered interior. But there's a surprise once inside.
In the exact center of the dome, there's a hole that brings in light. So you have all of these arches that are leaning together to form the dome. And exactly at the center, where they all want to lean together, Roman engineers take away the material and build a hole in the middle of the dome.
The 30-foot wide hole in the dome's center, called an oculus, is a huge compression ring made of stone, which in effect is a series of arches forming a circle. The horizontal forces of the dome, which keep the structure stable, converge at the top. It was a daring move by the Roman engineers. The Pantheon was an amazing achievement. But after the fall of Rome, builders would find other spectacular uses for the arch. By 476 AD, the Roman Empire had fallen. Later, medieval church builders would take up the use of the arch, building primarily with stone. Concrete would not reappear for almost 1,800 years. But the designers of the Gothic era used the arch in ways the Romans could have only dreamed.
The biggest advancement during the Gothic era was the getting away from the barrel-type vault and using more of an elliptical arch or a pointed arch. So from a visual perspective, it allowed the arch to be much taller. And the goal of the master builders during the Gothic era was to try to bring in as much light to the interior of the cathedrals as they could. So the taller they could make the arches relative to the width, they were able to introduce far more area of window.
The era of the Gothic cathedral also saw the use of less massive design elements. Continuing to strive for higher and grander, church builders developed new techniques to maximize their uses of the arch. Gothic cathedrals such as Notre Dame in Paris are lasting examples of the incredibly complex workmanship of the master builders of the time. Cathedral ceilings reached heights of up to 150 feet. As these arches soared ever higher, materials were used more sparingly to allow for this vertical growth, resulting in thinner walls, pillars, and vaults. But with this increase in height, intense forces were exerted by the soaring stone arches and had to go somewhere. The Gothic designers came up with an ingenious solution.
You still have to get the thrust of the arch down to the ground. So how do you do that? That's the real challenge in Gothic construction. And this is where the really ingenious breakthrough comes of building flying buttresses, which are exterior elevated half arches, really, that carry the flow of forces from the main vault down to the ground.
So as the arched ceilings grew wider and taller, the sides of the building wanted to spread. The use of flying buttresses provided a rock-solid method of reinforcement for the thin cathedral walls.
You can think of it as half of a Gothic arch. So a Gothic arch with a point at the middle. If you take those two sides and separate them, they each want to lean inward. And so they can help to resist the thrust from the central nave that acts between those two flying arches.
Flying buttresses became a very reliable method of building grand structures. But this method required precision. In some buildings, such as Selby Abbey in England, arches have deformed over time due to incorrect placement of buttresses. The flying buttress was perhaps the greatest inspiration of the Gothic era. After the Gothic period, as the Renaissance bloomed, the dome reemerged from its Roman origins to new and spectacular uses. In 1626, St. Peter's Basilica was completed just a few miles from its predecessor, the Pantheon. The new dome was 138 feet wide. Fable has it that the designers had intended it to be smaller than the Pantheon, out of respect for their forebears. But some modern scholars assert the Basilica's dome is almost 5 feet greater than the Pantheon's. But at 450 feet, St. Peter's was definitely much taller than any existing dome structure.
St. Peter's was significant because it was a very large diameter dome, very tall, dome being the revolution of an arch and over 360 degrees. St. Peter's was a grand application of the marriage of that round shape of the dome with the square geometry of the church below.
But the descendants of the Romans were not quite so masterful with St. Peter's. And within a few centuries, the dome began to crack as the tremendous forces generated by the height of the dome pushed sideways.
The original chain that had run around the perimeter of the dome was not sufficient to do the job. The dome was cracking, and they in fact needed to do additional strengthening work.
The addition of 3 more chains to retain the horizontal force of the arched dome was sufficient, and it has remained, damaged but stable for hundreds of years since. In 1965, the Houston Astrodome set new records for dome construction. At over 200 feet high and 710 feet wide, this giant leap in dome design was made possible with arches.
The wonderful aspect of dome action is that they allow the use of arches to create very large volumes of interior space. 300-yard football fields, 400 feet to center field, those are very long distances.
The Astrodome was made with a series of pie-shaped wedges that are built in steel, and you could picture it in some ways as a series of arches that are leaning on each other.
The point where these wedges meet is a giant metal ring, which acts as a keystone, completing the arch. The Houston Astrodome still stands today, but other domes took risks that ultimately didn't pay. Around the time the Astrodome was completed, another city began planning a similar project.
The King Dome is special because it's a pure compression dome. It was a concrete shell that was extraordinarily thin. And the problem with it is that such a thin dome over such a long span can have difficulties with buckling, the great flaw of any compression structure.
With its vertical spars and expansive interior, the King Dome served the citizens of Seattle for 24 years, but eventually closed because of water damage to its concrete roof. It was replaced with a new stadium that had a retractable cover, but for its time, it was one of the most daring concrete domes since the Pantheon. Domes continue to be used in modern construction to great effect, but the arch has found its way into other, sometimes surprising modern structures. And some arches literally do their jobs lying down. power of the mighty Colorado River is harnessed in the American Southwest by 9 main dams. 2 of these enormous concrete structures are examples of the arch turned to a new and critical task.
An arch becomes a dam when the arch is turned on its side and has the pressure of the water acting against it.
In fact, many of these structures are just that, a simple arch.
Arch dams are different than other dams because of the nature by which they resist the water forces. Most dams do so by the sheer weight or gravity. And arch dams do some of that because they have mass, but they're an arch tipped on its side, and it has arch action that thrusts the loads into the abutments, which are at the end of the arch. And those loads are resisted by the rock of the canyon. And they pretty much put the rock of the canyon into compression, which makes arch dams ideal for steep canyons, V-shaped, U-shaped canyons with good strong rock on either side, which is where you'll find most arch dams.
726 feet tall and up to 660 feet thick at its base, Hoover Dam was the largest concrete structure of its time. It required over 4.5 million cubic yards of concrete to build the massive arch. And it withstands the pressure of 9.2 trillion gallons of water in Lake Mead.
Because the water pressure comes from the depth. It's the hydrostatic pressure that comes from the depth of water that's supported. So, in fact, supporting a lake that's only 1 foot wide provides the exact same force that a lake that would be, 100 miles wide.
As dam designs became increasingly daring, relying more upon the strength of arches, dams became thinner and more refined. One such structure resides not far from Hoover Dam.
Glen Canyon is a beautiful arch. You can't deny that it's a very beautiful and magnificent engineering marvel. It's more of a thinner section. It's more of a true arch.
With a thin concrete slab 710 feet high and 1,560 feet long at the top, the dam relies on the shape and characteristics of the arch to resist the force of the water behind it, while using a minimum of material to do so. It's 25 feet thick at the top and over 300 feet thick at its base, and is extremely strong for its relatively limited mass.
The idea of the arch dam is to keep everything in compression and to minimize the bending that goes on in an arch.
And if the dam can avoid tension, the enemy of any arch, and stay in compression, it can last for hundreds, perhaps thousands of years. Dams are clear examples of the strength of the arch. But less obvious, yet familiar to us all, are tunnels, which use the strength of the arch deep underground.
Another example of arch action in which forces are redirected into compression is a tunnel. Many of us drive through tunnels on our daily commute. You'd have to ask yourself, where does the weight of all of the soil and rock above the tunnel go? It has to get redirected. It has to go around the tunnel. And it goes around the tunnel because of arch action.
While the Romans built small arch tunnels, the craft of modern tunneling really started in England in 1825, when Mark Brunel took on the great challenge of digging beneath the River Thames.
In the case of Brunel's tunnel under the Thames, that if he built just one large tunnel, one large opening, he was concerned about the loading coming from the sides failing the tunnel. And so what he did was he introduced a central pier with 2 kind of arches that were bearing on that central column. He was concerned about the size of the forces, so he cut the span in half by adding a central wall.
Brunel's innovative tunnel paved the way for something much bigger. Since before Brunel's time, engineers had dreamt of a tunnel under the English Channel, connecting Britain with France. This dream became reality in 1994. An arched cylinder was the perfect answer for the 31-mile run under the English Channel, up to 530 feet under the water's surface. These tunnels are 24 feet wide and are formed of a series of continuous arches, opposed to each other at an infinite number of points. In this application of the arch, The triple tubes are lined with a combination of concrete and iron compression rings, up to 23 inches thick. A cylindrical tunnel is an example of almost perfect compression, the best environment for an arched form. Just as the arch provides us access under the sea, so it provides passage over the sea. Without the arch, bridge building as we know it would be impossible. The wider the valley, the longer the bridge. And arched structures are often the best solution to that age-old question: how to get to the other side. Once again, the Romans got there first.
Visit Rome today, and it comes as a surprise to most visitors that many of the bridges in Rome are 2,000 years old. Among the most beautiful is the Ponte Fabricio, which is a wonderful example of Roman arch design.
One of the first arched bridges in the world. The Ponte Fabricio allowed Roman soldiers to cross from the banks of the Tiber River to an island in its center, 200 feet away.
The Romans, being excellent engineers and innovators, discovered through accident first, and then through continued experiment, that the concept of the arch could be used to great advantage.
The Ponte Fabricio was the first recorded attempt by the Romans to use an arch in a bridge. It continues to serve pedestrians in the 21st century. Since its completion, engineers have built tens of thousands of arch-supported bridges throughout the world. In the 18th century, materials such as iron became viable for bridge construction. The Coalbrookdale Bridge in England is an example of an early wrought iron structure. Completed in 1779 after only 3 months of assembly, it spanned 100 feet and was the first all-iron arched bridge. This beautiful structure was born of the Industrial Revolution and allowed for a light, airy appearance that greatly excited bridge designers worldwide. In 1880, Gustave Eiffel, later of tower fame, began construction on one of the first metal arch bridges in France.
Gustave Eiffel was a bridge engineer, and he built probably the most elegant iron arch bridge ever built, which is the Garabie Viaduct in central France. You had to have a long span, and you had to have it be stable side to side. So the Garabie Viaduct solved this by having a beautiful crescent-shaped arch, but then Eiffel flared out the base of the arch in the same way that he flared the legs of his tower 20 years later, in order to reduce the loading and make it more stable under the lateral wind load.
Completed in 1884, the viaduct spans over 1,850 feet and stands 400 feet above the river. It would inspire many bridge builders to lend an artistic flair to their work. The arch even finds its way into the longest bridges in the world, suspension bridges. San Francisco's Golden Gate is a classic example. The building of the Golden Gate was a landmark in civil engineering. It was completed with fewer injuries than any previous bridge construction and would span one of the most treacherous waterways in the world. By the time it was completed, the use of an inverse arch as a suspension element was well established.
A suspension bridge is exactly the opposite of an arch bridge. If we think back to the hanging chain, the loads on a suspension bridge are hanging down, suspending the roadway from a single cable or sometimes a few cables that are parabolic in shape, and they're pure tension. So if you wanted to turn a suspension bridge into an arch bridge, you would have to freeze those cables, turn them upside down, and put them under the roadway. The roadway of a suspension bridge often has an upward camber in the middle, a slight arching effect. And that's largely aesthetic, that it somehow is more comforting to the eye to see a slight rise in the roadway.
in addition to the huge cables that hold the bridge up, acting in tension. Many suspension bridges are still supported in part by the traditional compression arch. On the Golden Gate's south end, a large metal arch supports the roadbed as it clears historic Fort Point. Arch-supported bridges come in many forms and varieties. Some, such as the Bixby Bridge on California's Pacific Coast Highway, use just one long, shallow arch. This stunning span, completed in 1932, is 714 feet long and stands over 240 feet above the crashing waves near Big Sur. The roadbed is connected to the arch with numerous spandrel columns, or vertical braces.
Bixby Creek Bridge was built in the 1930s, and initially, when the bridge was put out to bid, the contractor had the option of constructing a steel arch as opposed to concrete arches. The thought being that the steel arches would be much easier to construct because they could be constructed from the roadway. They wouldn't be impacted by the waves or the creek down below. However, the contractor decided that it would be less expensive to construct the bridge using the concrete arch structure.
One advantage of concrete in such a bridge is its incredible strength.
An arch structure is primarily a compression element. The vertical load path of the bridge will go from the T-beam deck into each of the columns, and then from the columns into the arch. The arch will then take that load and distribute it to the two towers on either side of the bridge. That's the beauty of an arch.
Other spans have arches above the roadway, such as the Desmond Bridge in Long Beach, California. But this bridge is rapidly deteriorating and will soon be replaced with a design pioneered by the Natchez Trace Bridge in Tennessee.
This bridge is the first precast concrete segmental arch bridge in the United States with 582-foot span. The bridge is unique because traditional arch structures carry the load of the deck through a series of vertical members, which are called spandrels, that are then connected to the arch. In this case, the vision was to open up the arch and eliminate the spandrels. That way, the load of the deck is all carried at the crown of the arch. The arch is in fact independent from the superstructure. The superstructure sits on bearings on top of the arch, and it's the load that is transmitted from the superstructure, the top deck, into the crown of the arch, which transmits that load.
The Natchez Trace Bridge represents the state-of-the-art in arched bridge construction. And since its completion in 1994, it has become an emblem of modern bridge design. In the past, arches have served us in buildings, dams, tunnels, and bridges. And they will continue to serve us in our ever-expanding future. Not all arches are structural. The graceful form of the arch and the dome has captivated onlookers and users for thousands of years.
I think the arch is a consistent form that always recurs, regardless of material and culture. You can see it in almost every architecture in some form or another. It's very interesting to see its transformation in contemporary times into new materials and forms.
We're surrounded by arches that are primarily ornamental in function. Some are mere add-ons to contemporary architecture, while others are integral parts of an overall design. But perhaps no single contemporary structure makes a stronger statement than the Gateway Arch in St. Louis, Missouri.
Yeah, the St. Louis Arch is sort of typical in that from there you could see the way the shape of the arch is, where the loads are concentrated. If you look at it, you'll see at the very top, the apex of it is sort of a thin section, because there's not too much load being accumulated there, other than just the weight of that particular section.
Built between 1963 and 1965, this 630-foot high arch is a masterpiece of design. The legs of the arch are 54 feet wide on each axis at ground level, and taper to only 17 feet at the top. The massive foundations that support it were dug 60 feet deep, 30 feet of which extend into bedrock. The giant arch is supported largely by the outer skin, which is composed of stainless steel weighing over 900 tons. The arch was stacked out of individual metal sections. Cranes lifted each new segment toward the top until the last keystone section was placed. While the Gateway Arch must support itself vertically, it must also be able to sustain high lateral forces, such as winds.
So we have to make sure we have a thicket anchored where the arches end.
This giant arched form was as much an artistic statement as an engineering landmark that drew on a classical shape.
I think people are drawn to arches really just because it's a familiar form, mostly. It's something that you've seen throughout history. Almost every period has an arch appearing, and it's so familiar to people, that's what makes it appealing.
The St. Louis Arch is perhaps the ultimate expression of the arch as art. But the basic shapes of arches, domes, and tubes continue to serve us in a stunning diversity of ways. Even submarines use the power of the arch to do their stealthy work.
Submarines are pressure vessels that have to resist the great force of the water, particularly when you go deep underwater. The internal pressure just wants to crush a submarine. And so the section of the hull, the shape of it, is a circular shape that resists this pressure in compression. So you can think of a submarine as a circular arch.
The U.S. Navy's newest submarines use this tried and true design to dive deeper and prowl farther than ever before. Modern submarines are completely cylindrical, which enables the entire structure to become an arch in compression. And they use more arches inside, in the form of braces, to withstand pressures of over 400 pounds per square inch as they dive to record depths. In addition to the cylindrical shape of the hull, each end is capped with a dome, further strengthening the vessel. Modern submarine hulls can be up to 3 inches thick, and many are able to dive below 2,000 feet. This is accomplished by augmenting the strength of the arch with exotic metal alloys. These metals must combine the ability to become compressed with a tendency to be elastic, so that the cylinder doesn't fail under the crushing pressure. So in effect, the arches used in a submarine must survive both compression and tension at the same time. These advanced technologies may lead to the colonization of Earth's final frontier, the bottom of the sea.
We talk about extreme environments. One example would be under the water, where you have the structure acting as something that resists compression, because the water is very heavy and it creates enormous forces upon the habitat where people live. So in that case, they're acting as compressive structures, and they tend to be rather thick because they have to withstand the pressure.
But with modern alloys and composites, people should be able to live undersea without fear for years, even decades at a time. On dry land, the arch has been used for years in the design of semi-permanent battlefield structures, now used in civilian life, such as Quonset huts.
And all that was a big arch, elongated arch in one direction, and it was very efficient to put together very fast, and of course that military made great use of that.
The Quonset hut's strength is derived not just from the arched frames, but also from the multi-arched corrugated materials used to cover them. New designs continue to evolve, using this same time-tested shape. In another exciting application, the U.S. Army is experimenting with a giant inflatable arch, able to lift huge loads. These arches are also used inside giant inflatable buildings and may one day replace structures such as the traditional Quonset hut because of their increased portability and ease of construction. But the strength of the arch goes beyond the confines of Earth. For anywhere gravity applies, the arch will serve as a basic element of construction. On the cold, dry surface of Mars, arches, tubes, and domes may house the communities of the future.
The habitat pressurized space have the same laws of physics governing their design. And if we look at, for example, historic arches, they assume a certain shape because of laws of physics. The same thing happens in space. They're the same laws of physics that govern operations in space, but the conditions are often different. And over my shoulder, we have a model of one of the Mars-based scenarios that we've established that has a variety of different kinds of elements.
Most planned lunar and Martian colonies utilize tubes and domes in their construction. Some are inflatable, while others are made of hard plastics, composites, and metal alloys.
We work with geometries. Our curved shapes are usually pressure vessels. So they tend to look like cylinders, thermos bottles, those kinds of things, but they typically are all circular in section.
But some of the most recent and daring plans for colonizing Mars harken back to the Roman era, using local materials for arch construction.
Because it takes 6 to 9 months to get there, you want to use local materials on Mars in order to build. Well, what materials are available on Mars? There's essentially rock and dirt. This project developed an entire settlement on Mars, essentially a small city, made only out of arches and domes. It almost looked like an Islamic city from the Middle Ages. But it's what we consider to be the most high-tech solution to the problem of building on Mars.
These structures would become, in effect, tunnels, and house these interplanetary explorers under the Martian surface. Similar structures already house astronauts in Earth orbit, and via deep space voyages, will someday reach even further into the solar system. Our building blocks in space, just as those that have served us on Earth for thousands of years, will utilize the properties of that most basic of shapes, the arch.